Okay, we're ready to begin. Welcome to our Tech Talk today, Simcenter FLOEFD, simulating headlight condensation and thermal flow. Questions will be answered live at the end, but please feel free to go ahead and enter them into the chat as they come up. Our presenter today is Pratik. Pratik is an application engineer for Solid Edge and Simcenter 3D at Prolim. He graduated from Michigan Technological University with a Master of Science degree, specializing in design and FEA. Pratik is based in our Cincinnati location. Pratik, the Tech Talk is now yours.
Good morning, everyone, and welcome to today's Tech Talk on SimCenter FLOEFD, where we'll be simulating headlight condensation and the thermal flow. So this Tech Talk is continuation of my previous Tech Talk. In the previous Tech Talk, I discussed the electronics cooling effect and the thermal simulation for LED modules inside FLOEFD. So just in case if you missed that tech talk, you can go to our Prolim YouTube page where I've uploaded the entire video so that you can review it. Now, this specific tech talk is focused on the automotive headlight and the condensation effect. Now, if you have ever parked your car outside in cold and humid environment, you'll see that you'll see some condensation effect as shown in the screenshot. Now this normally happens because of temperature difference between outside and inside of the lens, where outside being colder and inside being warm and humid. And this warm environment can be because of the headlight heating or the engine bay heat flowing towards the headlight. Now, some of the prevention techniques in order to avoid the condensation is checking for proper sealing, installation of vent caps correctly, avoiding high pressure washes, and using silica gel packs specifically away from the bulb. And some of the regular repair techniques include drying of the headlight. So you can use either a hair dryer or a heat gun, sorry, and resealing the headlight, replacing cracked lenses or housing if that's the case, and upgrading vented or aftermarket housing. Now, this specific tech talk I'm doing using NX as the base CAD software, and the previous one I did using Solid Edge. My goal to choose the different softwares is to show how seamlessly does FlowFD integrate with both Solid Edge and NX. So this specific tech talk is SimCenter FlowFD for NX. Now the scenario that we are simulating here is that the car is stopped in cold humid environment, and after 750 seconds the LEDs are switched on, and after around 20 minutes the headlights are turned on, which is around 1200 seconds. The objective is to predict the transient flow and thermal distribution and possible formation of the condensation or ice on the inside of the lens, and then we'll see how turning on the engine and headlights and the heating effect takes away the condensation from inside of the lens over a period of 60 minutes. So I'm going to walk you through the entire setup process one by one. So the first one is wizard slash general settings. So let's jump into our software NX. So within NX, it is very similar to what you have seen inside Solid Edge. You have your flow analysis tab, and everything here looks exactly what it would look like. And to start a new project, you can come to a wizard and start by creating your project. So I'll just name this as condensation. Now I'll choose my units here since I'm more familiar with the SI units, and specifically I want my temperature to be in Celsius. So these are the only changes I'm going to be making inside my wizard setup. Now what kind of analysis types do I want to include here? So by default flow is included. I will switch this to an internal type of analysis. Then we'll turn on the conduction effect, radiation, Now for radiation, I will most likely be using Monte Carlo simulation, and my environment temperature here is going to be negative 20 degrees Celsius. So if you wanted to simulate the heating from sun, you can do that as well using solar radiation. But I don't want to simulate that right now, so I'll skip that part, but I'll turn on absorption in solids. So heating effect included for the solids surrounding the fluid, and for special characteristics I'll be using rays instead of bands and black body spectrum. And since this is going to be a time dependent study, I'll turn that on as well. I'll just keep the default time for now, and then we can later on change that from the calculation options. Use gravity as well, which is going to be negative y-axis. And that looks good. Next, we are going to be selecting our fluids. So our fluid here is going to be air. So let's do that. Air. And also inside the bulb, I have some inert gases. So I'll be using krypton as my inert gas, and I want my air to be the default fluid. In this case, I don't know what kind of flow type will be included, so I'll choose both laminar and turbulent, and let the solver decide that. Since we have some humidity inside, I will probably turn on the humid and fluid film, which will be film inside of the lens, and then I'll also turn on the film motion. Now for solids, I'm only going to choose one for housing, which is going to be nylon, and that should be in polymers, nylon 66. That looks good. Now since we have to include thermal effects, we'll be using heat transfer coefficient as a default outer wall thermal condition. And instead of using constant values, I would like to use time dependent values. And it's very easy to set that up as well. So you can simply come here and say choose this option called as fx, and instead of using a constant value, I can do it based on time. So here we'll specify time. At time 0 we have 7 watt per meter square Kelvin. Then at 1200 seconds, when our main headlights turn on, I'll have 7 as well. And then again at same time 1200, it jumps from 7 to, let's say, 80. Then it stays 80 for around like 1500-ish seconds. I'll still use 80. And then from there it maintains that all the way up to 3600 seconds, and I'll still choose this as 80. So basically when my headlight turns on, I'm increasing my heat transfer coefficient, and you can quickly uh, plot this using this chart option so that you can see how it actually looks like when you plot. And if you want, you can actually even remove this one right here, so it doesn't matter, because if it's going to be constant from 1200 to 3600, so I can simply remove that and just keep 3600. Similarly, we'll be doing for external fluid as well. So now the condition that I'm trying to simulate here is that my car was turned off at the very beginning. So when it started, the temperature was slightly higher, and this temperature was coming from the engine bay, which is 4 degrees Celsius. At 1200, it was still 40. Then again at 1200, now I'm going to choose this as negative 20. Now this is the outside temperature. It remains negative 20 for around the same time, which is 1480 seconds. I'll choose this as -20. And then at 1480 there's a jump all the way up to 25 degrees Celsius. Now this heating, this jump from 20 to 25, you can say maybe because of the heating effect of the headlights, and then it remains 20 all the way up to 3600 seconds. Now this is just a rough approximation. I'm not saying that this is happening in real world, but this is what my initial conditions would look like. So for my default radiative surface, I'll choose black wall and go on to the next one. Now for my initial conditions, I'll be using a temperature of 25 degrees Celsius to start my simulation. So I'll start with 25 here, and for solid parameters, I'll be using 25 as well. And for humidity, I'll be using 90% humidity because we have a humid environment inside, and a temperature of 25 degrees Celsius. Once you hit finish, the software does calculate, it's trying to recognize the internal fluid volume, and once that is done, we can move on to the next step. So before we move on to the next part, if you want to quickly check the fluid volume, you can do that using the options here. So you can do a check, which will give you the display of the volume inside, which is going to be the total fluid volume. And then we have another option that's called as show fluid volume, where you can see in the actual geometry the inside volume in blue. So this is going to be your internal fluid. Okay, so now we'll move on to the next part, where I'm going to be specifying the fluid subdomain. So let me hide a few things here. View, hide this one. So first, I'll go to my computational domain and check what it looks like here. So this is my computational domain. And then under fluid subdomain, I'll define my first fluid subdomain. Now, since the inside of these bulbs is not air but it's krypton, so I'll change my default from air to krypton. Select the outside face, which helps it to recognize the inside fluid. Oh, maybe not this one. It should be the inside face, sorry. Correct. So it helps us to define the inside of that lens. And then we'll keep the default conditions for now. For humidity parameters, I'll still keep this as default, 90, 25, and pressure, unless you know something else. And the name template looks good here. So instead of the number, I'll specify this as high beam. And we'll do something similar for the low beam as well. So I may have to hide a few more things here. Okay, that's better. And specify fluid subdomain for our low beam as well. And we'll switch this from air to krypton. Just make sure that my humidity parameters are still the same, which looks good. And change the format from here to lobby. So now that I have defined my fluid subdomain, I can go ahead and start defining the solid materials which I'll be using. So let's start with the first one here. Let me hide this again. So the first one which I'll be defining is going to be the inside of the filament here. So create a new solid material, and the body is going to be on the inside, which is the tungsten filament. And in my predefined, I'm pretty sure I have tungsten under metals, which is right here. Looks good. So here we are just going to name this as tungsten for filament, and we can do this for both the lengths. So these are both of my both the filaments for high and low beam. Then the pins to which this filament is attached is made of molybdenum. So I'll go ahead and create that as well. So this is the first pin. So it's those three parts there, and also the small part right here. This is made up of molybdenum. And we'll do the same for low beam. So it's this one, two, three, and four parts. Okay. Now, once you have specified the filaments and pins, we'll move on for the bulbs. So let me do a show all again. And then I'll just hide this one, this, and this one right here. So now my bulbs are made up of a transparent material. So let's find that one. So I'll specify this bulb and this bulb, and also the low beam lens. And this is made up of quartz. So which is under glasses and minerals. I'll select the quartz class, and here, since these are transparent, I'll turn on my absorptive radiation transparency, which is most likely used specifically for ray tracing, since we have Monte Carlo simulation and rays, so we can see the light coming outside from the bulb. So we need to set a radiation transparency as absorptive for these ones. And then the bulb tips here, if you see, they're coded in black, so we don't necessarily need the absorptive for those. So again, I'll have to specify those separately. So again, I'll select these two bulb tips and use the same quartz glass, but this time I'll keep them as opaque. Now the next one here is going to be the outer lens. So let me turn that on. The outer lens here is not made up of glass, but it's a polycarbonate material. So we'll try to find that one. So outside lens should be under polymers, and we can choose polycarbonate. And here again, I'll have to turn on my absorptive for that material. The next one is going to be the bezel, which is in black here. So this one is also made up of polycarbonate, but we did not define that with the lens because we want our lens to be absorptive and this one to be opaque. So we are going to define that separately. Polycarbonate black bezel. The housing here is going to be nylon 66, which we defined earlier in whilst heading up the study, so we don't have to specifically define that again. The next one, which we'll be defining individually, are going to be these screws. This is screw one, this is the second screw. I think it's made up of some kind of stainless steel, and also the bulb tips here, or not the bulb tips, the bulb base is actually made up of stainless steel as well. So let me hide a few things here so that I can select it properly. Okay, so solid material, it's just 1, 2, this 3 and 4. So these 4 parts here, they're made up of stainless steel 302, should be alloys. Bulb base and screws, stainless steel 302. The next one, which I have to still define, is we have some PCBs for the LEDs here. So let me go ahead and define those. So I have these 4 PCBs, 1, 2, 3, and 4. So I'm going to be defining those separately. So solid material, and specify the solids here. Under predefine, I think I have, let's see, it should be under non-isotropic, and the PCB4 layer, and do that right here, PCB4 layer. And there is one last component which I have to define, is the heatsink for those LEDs, and that's made up of aluminum 6061, which is this one right here, and that is the last solid material which I have to define. That should be an alloy aluminum 6061 heatsink. So this ends the definition of all the solid materials for this specific simulation. Now the next step is where we start defining the boundary conditions. So the boundary conditions here include the vent. So if on the back here we have a vent, so we can define an environmental pressure on the back face of that vent. So let's start with that first. So flow analysis, boundary conditions. So we're going to be defining environmental pressure on the back of that vent face. which is this face right here. So I'm just going to be defining the type. I don't need the number because this is the only one we have, that is environmental pressure. Next, we'll be defining some wall conditions for the lens. So let me hide, or let me do a show only on this lens. Now what we are going to do is we are going to define an outer wall condition on the lens. Now the reason why we're defining the outer wall condition is that this is the only medium through which that negative 20 degrees Celsius temperature will be coming in, or to signify that temperature difference. So let's start with that boundary condition. And for wall conditions, we'll be using outer wall, and select all the faces that you can see here. Also these smaller faces which may be slightly hidden, so we have to include those as well. Okay, so now once you've defined the outer face, okay, let me select these ones as well. Okay, that's better. Now once I've defined the entire outer wall of the lens, now instead of using the existing heat transfer coefficient, I can either define my own, or and I can do the same thing with the temperature. So I'll just keep this heat transfer coefficient as default, which is coming from what we have specified, but the temperature I can control here. Oh, so the temperature here, as you can see, is going to be dependent, but if I want, I can control that and have a constant value. So instead of this, I can say use a constant value, that is negative 20 degrees Celsius. If you scroll all the way up, we can say negative 20. And for heat transfer coefficient, instead of using this one, I can use the default. I can delete these two rows because I don't want them. And at 1250 seconds, I'll increase the heat transfer coefficient. Instead of 80, I'll just make it as 20. So these are my outer wall conditions, which you can specify individually on the outer lens. So you can think of this as a local override. So this is my outer wall. So it shows these like square-like symbols, which is an indication of the wall conditions. The next one I'm going to define is a real wall condition for the black tips, or the bulb tips. So let me bring back my entire model here, and boundary condition, we'll insert a new one, and for wall conditions we'll specify real wall. Oh, sorry, I did not select the specific one. So it's quartz bulb tips right there. So these are the boundary conditions which I was planning to specify. The next condition which I also want to specify here is the film condition. So film condition is where I can specify the wettability and the faces on which the condensation film will appear. So let me do a show only on the lens. And now here I can specify film condition. From the boundary condition drop down, you'll see film condition. So all I have to do is simply select the inside faces where the condensation film will be appearing, which is all of these inside faces. So once you've specified all of these, the next step is you have to turn on the wettability. And if you know that there is a very small thickness, you can specify uh, an initial film thickness as well, which in my case it's not. So you can just simply skip this one and just use 0 and turn on the wettability. So this is the film condition. This is how you specify that. And one last step here for the boundary condition is we have to specify a perforated plate. So let me go ahead and bring my model back up. And before I specify that, I would like to show you what it looks like. So I have a user-defined perforated plate, which I'll be using here for this headlight part. So if you go to properties, I have specified the loss coefficient and the hole shapes as you can see complex. Now this is the user-defined perforated plate which I plan to use. So again, if I come down to the film condition drop down, I can specify perforated plate. So this is just the initial message saying that you have to select the face which you have used for environmental pressure or fan. So in this case, we don't have a fan. We'll select environmental pressure, which brings up our regular menu. And once you do that, you can turn on my user-defined vent membrane and select the perforated plate right here. So this is how you specify all the boundary condition. So looks like we skipped a few of these. I did specify the computational domain. We finished the material definition, and then we specified the boundary conditions. Now the next one is where we specify loads. So here loads as in are the thermal loads, where we can specify temperature, heat generation rate, radiative surfaces, radiation sources, and so on. So let's start with that. So the first load which we're defining here is the thermal load. So from this drop down here, I can select volumetric heat source. Now in this case, I'll be doing two different ways. I'll be defining a volumetric source for high beam and then volumetric source for low beam. So if I do a quick pick here, I should be able to select that specific option. And now we know that our volumetric heat source only turns on at 1200 seconds. So instead of keeping it on all the time, I can define a dependency and use the values. So at 0, it's off. At 1200 second, it's off. Then it turns on at 1200 seconds when the headlights and engine are turned on and stays on for the entire analysis. You can also plot like we did before. And here I'll be defining that as a temperature, which is 2626.85. and this is going to be volumetric heat source for high beam. Now similarly we can define for low beam. So just to save some time, I'll just copy it from my existing study for the low beam. So copy to project for condensation. Now once I've defined that, I'll move on to the next step where we define the radiation sources. So on this, in the same drop down, I can define radiation source. First, I have to select which specific entity, which in this case is going to be high beam. What type of radiation is it? Is it diffusive or directional? And is it turned on always? Or if you want to make that as a time dependent, which is what we did for our volumetric heat source as well. So at 0, it's off. 1200 still off. And stays on for 60 minutes. Now here I can define it as a temperature, intensity, or power. So I'll just use 25 watt and define this as high beam. Similarly, we can do for the low beam as well. So just to save some time, I'll go to my existing study and copy it over from here. So copy to project condensation. Now the next step is where we define the radiative surfaces. So let me hide this face or this part here. See, we'll hide this one. Okay. Now you can define the radiative surfaces from here. So the first one that we are going to define here is the reflector. So we have this one reflector over here. So I'll choose the solid body. Same thing over here as well. I'll choose this one and this one. So I've these three reflectors, and I have a user-defined reflector coating which I'll be using as the reflective surface material. Next one is going to be the white body filament. So these two filaments which you see are the next radiation sources. Oh, sorry, radiative surfaces. So again, go to radiative surface. I can choose it from the solid materials here. So high and low beam. I can choose both of them. So these are all the surfaces. As you can see, it's highlighted on the window, and then I can define that as white body wall. And the third reflective surface is the bulb base here. So these two bulb bases, these are the third radiative surfaces. So insert that. Which is this one and this one right here. And we can use an existing real surface. So since these are made up of stainless steel, we can use some kind of steel here, which is steel polished. And just like that, we can define the radiative surfaces. Now the next part is where we define the LED sources. So let me hide a few things here again. Oh, not the clip section, hide. Now the way you define LED is quite simple. If you come to the drop down, go to LED. From here I can select the top faces here. So my top faces are going to be this one and this one. and the bottom face of the LED, which is this face right here. Oh, sorry, it has to be actually in the second one. So the second one here is where I select the bottom face, and then automatically identifies the entire LED module. I can use the existing predefined LED modules, and again, just like our heat sources, we have the toggle option. So if you remember from the slides, we know that our LEDs turn on at 750 seconds. So we'll try to define something like that. So for 0 it's off, for 750 off, at 750 it turns on and stays on for 3600 seconds, which looks good. uh, which has a current of 0.2 amperes, and everything else here, the duty cycle, solid temperature, looks good. So I'm just going to name this as LED1 and save it. And similarly we can define for the two other LEDs as well. So just to save some time, I will copy this from the existing project. So this pretty much covers our setup for loads. So first we started with the computational domain, then we specified all the solid materials, then the boundary conditions, film condition because we had to specify the condensation effect, then the volumetric heat sources, which is the filament of the two bulbs, then the radiative surfaces, which are going to be radiating heat outside, then radiation sources, vent membrane for our vent hole, and the LEDs. So we are very close to finishing the setup. Next, we have to specify goals and finish the meshing. Now, the next step is where we define the goals. So let me go back to NX and turn on all of my parts or bodies. Now, the goal definition process here is very easy. So first, let's start with global goals. So what kind of global goals am I interested in? So the first one, let's see, I want to take a look at average static pressure. Then I would also like to see fluid temperature. Then average velocity. Then I will take a look at heat transfer rate and net radiation rate. So these are all the global goals that I'm interested in. Next, we will now move towards the surface goals. Now, since we are more focused on condensation, we'll have more goals defined for the inner lens or the inner lens face. So let's go to goals here and say surface goals. So for surface goals here, what I can do is I can start by specifying the existing inner lens, which is using this film condition. So it automatically selects the inner lens and I don't have to do anything else there. Then some things that I'm interested in is film mass, then the lens film, then mass flow rate, total mass leak, film thickness, max film thickness, film mass flux, film growth rate. Uh, yep, that looks good. So these are all the inner lens, the inner lens surface goals. Then the entire outer lens. So we have some surface goals defined for that as well. We should do that. So I'll do that using the outer wall parameter. So it automatically selects the outer wall of the lens. Then here I'm interested to see what's the solid temperature of the lens. So here specifically we'll just take a look at average temperature and max temperature solid for the lens. Then we will also review some of the volume goals. So for volume goals, uh, I want volume goals for the entire lens, and we will be focused on temperature solid. Max solid temperature for the lens. Then we will do volume goal for the bezel and max solid temperature. Then we'll do the same for housing. And then finally reflectors. So I can choose the reflectors from my radiative surfaces, so reflector coding, and try to converge that for the temperature solid. So these are all the surface goals that I'm interested in. Now we move on to the next part and the last part of the setup, which is meshing. So here we have our default global mesh, which somewhat looks decent. But the problem with this global mesh is that it does not actually cover all of these smaller parts. Like if you see as compared to the mesh here, we have a very small filament, we have a very small bulb tips and small crevices and surfaces like that. So in order to achieve a very good control, what we should do is we should define local mesh in that area without affecting the global mesh. So I'm going to keep my global mesh settings as they are for now. I don't want to change anything here, and click OK. And I'm going to hide this just in case something comes up. Okay, so let's start with the inside filaments. So since I have two filaments, if you right click on the mesh, you have this option called as insert local mesh. Now here, when you insert a local mesh, you have two different options. You can you do it using reference objects or for a specific region. So here what I'm going to do is I'm going to do it for reference first, and for reference I'm going to select the tungsten filaments. So those two solids are here. Then what I can do is I can start refining the cells. Now what kind of cells I'm interested in? First of all, solid cells. So I can move the slider to the right by trying to increase it to which will create a very small refinement in those areas. So let's say I want to move it all the way down to 8 because I want to capture the gap between the two as well, which is and all the fluid solid interface objects as well. So we're going to use these settings. Now once we did this with the filaments, we will do the same thing with bulbs, lens, the outer lens, and the reflectors. Now to save us some time, what I'll do is I'll copy the local mesh from my existing setup, but the process is exactly what I did. You simply come to the mesh, right click, go to local mesh, and within the local mesh you select the specific object, which then lets you control the local mesh in that area. And if you scroll down all the way, you have an option to display the refinement level as well. So here you can see how small or large of a mesh you have created. So that looks good. Next, I'll go to my existing study and I will bring in all the way from bulb to LEDs and copy this to my existing project. So this is how you create mesh using sorry, yeah, using the reference model. Now the second option that we have in the local mesh is using reference shapes here, which is a region. So now by default it goes to cuboid, but I can specify that to sphere, and then I can also specify which region needs that refinement. So I can use this arrow for sphere and then increase and decrease the size of the sphere like this. If you feel that your sphere covers the area in which you want the refinement, this also is a very good technique to do that. And then I can define my refining cell, so I'll just say refine it up to 3 for fluid, solid, and fluid solid interfaces. Then I can specify my max channel refinement to 4, and then small solid feature, maybe I don't need that small, so I can just do it maybe 3 or 4. Curvature, maybe slightly move it to 3. And then if you want to specify tolerance, I don't need such small tolerance, I can just keep it at 1 if I want. So this is how you define local mesh using reference and region. Now one more thing that we have to do before we run the simulation is that we have to check the calculation control options, and this is especially important when you're trying to do a transient study. So here our physical time is not 1 second, which we initially defined, but it's 300 seconds. So you can control that from here. When do you want the simulation to stop? If one condition is satisfied or all conditions satisfied. If you want to specify the number of iterations, you can do that from here, or the calculation time. Then what goals do you want to check the conversions for? If there are certain goals that you don't want to see the conversions for, you can simply uncheck that, and those goals will be removed from the convergence criteria. Then under refinement, we have already specified the refinement here. So if you still want to control what level of refinement do you want for the local meshes, you can do that from here. Then under solving, here by default you will see an automatic time step, but it will take days and days for such complex studies. So what I like to do is I like to specify a manual time. So here I'll specify, let's say, 0.05 seconds. Then one other thing which you can also do here is when you go to the saving tab, how often do you want to save the results? Now what I like to do is, instead of iterations, I like to do this as time. And since my study runs from 0 to 3600 seconds, I like to save my results every 600 seconds, let's say, for example. So we have 6 different times where our solution will be saved. And then if you're trying to do a transient study, what kind of results do you want to see in your transient study? So if you click on those 3 dots, you can include mass fraction of water, mass fraction of air. If there's something under radiation that you want to check for, net radiation flux, and so on. So these are some of the things that you can do within the calculation control options. And then once you have specified all of these things, you can go ahead and run the simulation. Now the last part is that remains is to review the results. So let's take a look at that. Now here I have already loaded all the results. So first let's take a look at the mesh here, and let me hide things so that we can see things clearly. So if you see here, the blue area, which is the fluid mesh, which is our default mesh, is what it looks like. And if you zoom into, let's say, in the bulb area, maybe I'm having some graphical issues here, but the red area indicates a refined mesh here in this region, something like this. So our mesh refinement looks good, with red indicating the smallest mesh and blue indicating the largest mesh. Then we will also take a look at the flow inside the model. So, and just to see that flow clearly, I'll just clip this section so that we can see how it's going or what's going on the inside. So I'll turn on the flow here. So this is what the flow looks like, and so this is the flow plot for the temperature, and it would make sense because we have higher temperature in the area where the bulbs are located, and as you go away from the bulb, the temperature goes on decreasing, which makes sense. And if you play, you'll see this flow going on inside the model like this. And one other thing which I have also plotted here are the rays. Since we did a ray trace study, uh, we can show the rays coming out of that specific lens. And if you see here, since we have set these as reflectors, the rays reflect from the reflectors and they pass through the lenses. So this is what the rays coming out of that bulb would look like. Now these all results that you just saw are steady state. Now let's take a look at the transient results too. So in order to load the transient results, you have to right click on the results and turn on Transient Explorer, and this will show all the results which you have selected while you're specifying this under the calculation options. Now first, let's take a look at the lens temperature. How does the lens temperature vary over the time? So here it goes all the way from -20 all the way high to 120 degrees Celsius. So if I hit play, you'll see the temperature in the lens changing. Then the next part which I would like to also show you is the film thickness and surface temperature. So if we turn both of these on, what you will see is the condensation happening on the lens, and what does the temperature look like before. And I'll just hide my model here real quick so that we can see things clearly. So once I hit play, at the very beginning you'll see the condensation forming, and then eventually as our bulbs turn on, it evaporates and you'll see less and less of the condensation. So this is the entire plot of the study, and if you see, the condensation starts to disappear exactly around 1200 seconds, which would make sense because that's when our bulbs are turned on. Now, if you want to view the results in between, let's say in between 0 to 3600 seconds, you simply have to right click, turn off the Transient Explorer, and then you'll see this option called as load time moment. So from here, so these are all the results that the solver saved, which we specified under the calculation options. So we have 0, 600, 1200, 18, 24, and so on. So if you want to view any intermediate results, you can click that specific time step and review the results at that specific time step. So let me jump back here. So this ends the presentation. Now what we did here is called as a combined approach, but there are two different approaches that you can take when you're doing any kind of headlight condensation simulation. So number one is you can split that approach into soaking and then condensation, where you do two or three separate runs, where the first run is basically your soak or preconditioning, where you bake and then expose it to humid environment. This is optional to simulate. It is generally used to preload the lamp with moisture, and then you can run a cold soak where you cool your headlight assembly to negative 20 degrees Celsius. In this case, you don't really need the fluid film on, which is just going to complicate things and it's unnecessary there. And then you do the last one, that is condensation and film, where the lamps turn on and also your film is turned on. Now this approach is more modular. It matches what most of the OEM test protocols indicate, and it's very easy to restart, and each of these runs are dependent on one other. And the other one is what we just did, which is a combined approach in a single timeline, where we heat the underhood, then we cold soak, and then we reheat. So all of that combined into one, we can is what we have done in this specific simulation, where we consider lamps turning on and then we turn on the humidity and film as well. Now, the second approach is more realistic vehicle history, but sometimes it can get complex to simulate both cold soak and condensation at the same time. So I would like to thank you all for attending this tech talk.